Hello, good afternoon. Welcome to another Sunday Essentials of Compilation stream. Today I plan to take a little detour. Um, the the book that we've been working through does not have a front end to the compiler. What do I mean by that? See, typically in compiler construction, you talk about the different phases of the compiler as being part of the front end or the back end, and then sometimes incoherently the middle end. Um, Middle end is usually talking about certain kinds of transformations that you might make on the intermediate representation so that it can be better compiled to better machine code. Um, and other sorts of transformations that like implement semantics and so forth. So, um, but the book that we've been working from is very well, not completely, but mostly bottom up. So you're going from the back end. You're going from you're building things on top of x86 assembly, um, and uh, and the idea, which is a great idea for comprehension as well as I think maintainability, is that you start with a very small number of features that you know exactly how to implement in assembly, and you add more features on as you go, so that like it doesn't feel like this huge overwhelming task. You can start with something small. You can build and test and verify, um, and then add more complex features on. But the approach of the book does not cover any of the lexical analysis or syntactic analysis, also known as parsing, and that is deliberate. Partly because there's a ton of literature out there about lexical analysis and parsing, and they're actually pretty straightforward to write, and they aren't particularly concerned with turning the semantics into machine code, right? They're concerned with interpreting text as data. Which, if you've worked in software for any number of years, you'll know that a lot of work in software is taking things that are as text or as binary formats, and turning them into something that you can structure your logic around. For example, taking a string of digits and interpreting them as a number that you can do arithmetic on is a very common thing. So that it was intentional by the author that there be no discussion of lexing and parsing. However, as we've been working through this series, gosh, we're up at like 14, 15 episodes now. I've felt the pain. Every time we want to write an example, you may have noticed I'll be writing in comments. This is kind of the pseudocode, or maybe it's like the actual code in a concrete format. But when we write a test example, I'll write that in a comment, but then I'll write out the syntax tree by hand. And I think that we're getting to the point where that it's going to be a lot harder to make good examples if we're always writing the entire syntax tree. And some of it is that we have structured the syntax tree in a way that requires us to write a little bit more data structures in order to get the types that we want out of it, right? So a good example are primitive operations, things like arithmetic, the read int, function that is implemented in a very low level, and Boolean logic. Those things, they're all primitive operations. So in other words, they're built into the language. They're not functions that you can call directly, but they look like functions at the concrete syntax level. The way that those are structured is that they're in the expression non-terminal. There's the prim version, which contains a primitive operation and all the variants of those primitive operations. So we get a little bit of verbosity there, where I'd rather not have it. So that is all to say, today and maybe next week if necessary, but I think we might get it done today. I'm going to look at some options for how to create a front end for our compiler. This is also in service of my other planned side quest, or interlude, which is to make a compiler playground. So not so much that you could compile and run it, but at least we could put the entire stack of our compiler into a web page. Because that's one of the advantages of Gleam, right? It compiles to both to Erlang and to JavaScript. So we would be able to embed it in a web page and not have not have any backend for it. It could just be running in your browser, which would be pretty awesome. So let's get to it. I have pulled up the Gleam packages page, and I just put in parse because this is what we want to do. There's not much here yet. There is one library which I want to pin and we'll probably use. It's called Nibble. It says a string parsing library combining a traditional lexer with parser combinators. So hi, welcome to the string, Anita. Gleam is a very cool and intuitive language. I love Gleam. Gleam is just, it makes me happy. So welcome to the stream. So we may make use of this. I haven't completely grokked the parse. I've looked at their docs. I haven't completely grokked the parsers yet. The lexers is fine. Like that's typical. So we'll pull that up. We have some other options that we could use if we don't want to be pure Gleam. It could present us some problems in that we wouldn't be able to necessarily get them to run in the browser. And I wanna call these out because first of all, some of them come with OTP. And sorry, that's small. So if we look at the application is Parse Tools, there's two modules in OTP. One is called Leaks. It generates a lexical analysis thing. So basically it takes your text and turns it into tokens. Yeah, I mean, you can hand code a parser too. I'm not, there are pitfalls to it that I may want to avoid, which is why I'm tending to wanting to use a library. And there's also Yek, which produces an LALR parser. So I don't want to spend a whole lot of time talking about the design of parsers, the technology in there. Just know that this abbreviation means look ahead, left to right, rightmost derivation. I think that's correct. And it says one, but I think that historically, Yek, you could tell it how many tokens it might need to look ahead. So that's what that one means, is how much look ahead does it need to use to determine the next branch to attempt. And the other thing about LR is that LR is not a recursive descent parser. So when you say recursive descent, what that means is like when you look at the next token, you determine which branch to attempt. Recursive descent will go call the function that implements that non-terminal, right? For LALR parsers, what happens is you start pushing tokens onto a stack until it matches a non-terminal from the bottom up. LL parsers are top down, so they go, what's the top level non-terminal in your language, and I'm going to attempt to figure out which branches of that non-terminal to take to construct that top level non-terminal. Yak, Bison, like these parser generators use a bottom-up strategy. So they try to match the lowest non-terminal from the terminals. Okay, and it pushes these tokens onto a stack until it matches, and then it like coalesces that, and then tries to find contexts within which that particular non-terminal will fit. So that's why they say it's bottom up. There are more efficiencies to LALR parsers than LL parsers. But anyway, so that little tangent there. So the disadvantage of using these is that it will generate Erlang code. We will have to write FFI to the Erlang code and keep updating the Erlang code when we change our Gleam code. And I'm fine writing Erlang. The big question in my mind is, do we get into, if we want to have a JavaScript backend for this as well, not backend, if we want a JavaScript target for this compiler, am I going to find things that are comparable to these two tools in JavaScript? I have a feeling we might, but also there's going to be enough differences that we have to do double maintenance. The other possibility here, shameless plug, is a totally different type of parser, which is, and this is also Erlang, which is a pack-rat parser generator, or it uses PEG, parsing expression grammars, as the grammar. It's a bit more like if you leveled up regular expressions than building an entire lexical analysis and parsing separate steps. It has some potential advantages over the traditional forms, but I wrote this library when I was new at Erlang. You can see 16 years ago. This is a long time ago. And there are some flaws to it. Flaws I've been unable over the years to remedy. So I would rather not use this. It's something that I keep going, yeah, that's the project I could do. I could go back and rewrite this in a way that actually works and is better. But I have not gotten there. Crazy, right? 16 years, my goodness. Yes, I started learning Erlang in 2008. So this was a project I started in 2009 at Erlang Factory 2009 in Palo Alto. Long ago. Anyway, so those are some options. I think I do want to go with this Nibble library. We're going to try it out. So it's inspired by Elm's parser, which is cool. So let's take a look at the example here real quick. And again, the advantage of this, even if like we maybe produce a parser that's not highly optimal, because this is using combinators as well as what like Neotoma uses combinators. The advantage is, of course, we only have to maintain one. So let's look at this example. So here they're saying, this is the Lexer. The Lexer, it's using simple. We'll have to look at what the other options are. I think the advanced maybe lets you control the context attached to each token, but there's some built-in token generators, so a number, right? And I believe what happens here is this is the combinator, and this is the function to call to construct the token. So what's happening here is it's taking the contents of this integer that it's parsed and putting it in this variant of token. Okay, and then here's a more low-level one, which is like, if you match this token, give me L per n. And these have no contents to those variants, so obviously it's just like, just construct this thing. Okay. And then, you know, white space, ignore it. That's going to be pretty typical here. Okay. So then when you have tokens, you build up combinators, which are your non-terminals. So here's an example, parsing an int. And it's saying, you know, this is the use syntax. We may talk about that in a bit. But this is saying, you know, take a token and pass it through this function, and if it's a number, then return yes, that number, otherwise return none. And I think this take map says if this is none, then this will cause an error to be displayed here, and that's what this expected number. Yeah, Nibble looks really good. I like the form of it. It feels good. Okay, and then they make a simple parser, which is, you know, parse an open parenthesis, parse a number, parse a comma, parse another number, parse a right parenthesis. So this is only parsing two numbers and creating a point structure. So one thing that we'll want to look at here is what other combinators are there. I think that we'll want things like many, so like repetition is a pretty common thing. You don't usually write out all of the things here unless there's a, what am I trying to say? Unless there's a static number of things. You often have repeated tokens or tokens with separators, that sort of thing. So we'll have to look into that. Okay. So, and this return is kind of like monadic return. It's like, here, this is, you take these things and you stuff it into this, and then it goes back up into your parser monad. Okay, so here, let's look at the module nibble. And yeah, so there's one of, which is like a list of options. That will be useful. There's things that are optional. And it looks like loop might be what, or many. Okay, loop is probably the lower level, and many is like one of the combinators. Okay, so if we're parsing it with a separator, use sequence instead. Right, and so this is like any number, including 0, and many 1 asserts that there's at least one element. Okay, and so map looks like it's transformed the output of this parser into this. So like the internal value of that parser changes. That's what map does. Let's see. Okay, and return. Okay, so this consumes no tokens, always produces a given value, sometimes called succeed. So this would be when you have done all the steps, then you can use return to be a parser that just returns the result. It doesn't do anything. It just says, here's the result. Okay. Okay, so they're saying use return unqualified when using do, and Gleam's use syntax, and nibble succeed in a pipeline with them. Okay. Okay, so run is what you call when you have your top level parser and you have your tokens. Okay, which this makes sense. It makes a result of whatever you expect the output of that parser to be, or a list of dead end, and that's okay. So these are the backtracks that it tried and failed, I guess. Okay. Okay, so here's the sequence one. The nice thing about this is, I don't know if you all have seen nom from Rust. It feels a little bit like that, which is cool. And that making it feel really, really familiar to me. Okay, so then there's take at least. Take map is what we saw in this example. It says take the next token and attempt to transform it with a given function. This is useful in creating reusable primitive parsers for your tokens, such as take identifier, take number. We'll probably make use of those. Okay. I think we have enough here. I'll keep these docs up so we can look at them. I think we have enough here that we can get started on creating the parser for our language. So remember last time, our top level language currently is elif. So this is the Lisp-like language with Booleans and conditionals. And we made this program here, right? And I think this was from an example in the book, and we didn't write in the comments what it actually was, but let's translate back. So this is like let y, and this is if true, read, otherwise if. I think we were doing this to demonstrate that we created blocks for dead code. We might go back at some point and optimize that. But here, if eq question mark read 0, getting pretty deep here, 777, otherwise another let, like I said, this is getting deep, read, and that's plus 1x, and then way out here in our let. So this is Gleam, but the language we're compiling is Lisp, is a Lisp. It's loosely based on Scheme. The original book is in Racket, so that's part of the. I think part of the reason why they do a Lisp is that Racket just has tools you can read a Lisp-like language into a syntax tree really easily. So I'm assuming that's why they do that. Okay, so this is plus y2. So this is the. And I'm going to probably break this out a little bit so you can read it better. Okay. Because this has a lot of branches in it. Right? Okay, so maybe that's a little bit easier to read. Yeah, eLisp is great. As a Lisp, it's fine. The hard part is Emacs, actually, with eLisp. You might, if you enjoy Gleam and you like Lisps, you might enjoy LFE, which is a Lisp flavored Erlang. It compiles to the Beam. Okay, so this is this program, and what we want is this to be the output, right? So let's we'll put it in passes, and I'm going to just call it parse. There's not a good reason not to. So let's, oops, hello. Okay, so I get all my homebrew updated. So let's Gleam add nibble. Okay, so we have nibble in our thing now. Okay, so let's look at the example again. So we'll want nibble lexer. We'll start with that. I think that's a pretty good place to start. Import nibble lexer. Okay, so I'm going to make a function called tokens, and it's going to take input, which is a string, and it's return a list of token. Except I think it's going to return a result, a list of token. And let's make a Lex error type. Okay, so we're gonna make a token, and that's gonna have some variants. We'll figure out what those are in a minute. And we'll make a Lex error, and we don't know what the variants are on that yet either. But we do have enough, to say, you know, these are the types we'll use. The main reason I'm doing this is I want to be able to write tests for our tokenizer. So like I want to be able to take this example that we have in our top level here and go, I want to make assertions about the tokens that are in this. Okay. So tokens that we're going to have. We're going to have L parens, and we're going to have right parens. Obviously, we're in a Lisp. We're going to have an identifier. Which is going to contain a string. Right, so we have like variables. Those are identifiers. We're going to have a... Now here's a thing that we might or might not do. Let's have let's have an integer which has an int in it. Let's have a boolean which has a bool in it. Those are literals. And then I think I want to say that we're going to have operators for these symbols like plus, minus, divide, times, etc. There's also something where we might want to we're going to have some back and forth. Let me put it that way. We'll have some back and forth of, do we want the lexer to decide that things like let and if are reserved words, so to speak? Yeah, that they do say it can be easier to implement a parser for Lisp-like languages, but I think that we encounter some of the same problems that you do for other languages. And actually the big problem here is that special forms. Essentially, like if is a reserved word, but in the lexical phase, it looks like an identifier, right? Because this could just as well be a function that you call. But what happens underneath is this gets turned into something else, right? This turns into, evaluate the condition and then branch, which is not at all what a function could do. So we need to possibly take special care. And let also has special meaning in that, like, once you use y here, it's available for this trailing expression as an identifier that you can reference. But a function can't do that. There's the other weird thing here in that, like the examples in the book, for instance, and I want to look at this first paragraph real briefly in a minute, but the examples in the book, when you use let, like, let's see if there's an example here. No, they don't have it in this one. We added variables in chapter 2, I think. Yeah, so when you use let, they use open paren, square bracket, and square bracket on the other side as well. I don't know why. I'm not sure why it isn't just parens. It could be that there's some implication that these are a set of pairs. but I don't know. This is like a scheme bracketism or something. You'll note that I think in eLisp, Anita, you mentioned in eLisp, you were looking at that. I think that they just use square brackets. I don't recall exactly, but like there's let, and of course there's let star, which lets you chain lets. It's actually kind of a macro. But this, I don't know why this is like this, for instance. Anyway, we need to take advantage of it in our, or we need to like handle it in our parser. So let's do a thing which is we'll call it L bracket and R bracket, but I almost want to combine the parens and the bracket into a single token. Maybe we don't have to do that yet. Anyway, something to think about. Real quickly, let's look at this. I think we covered this in the very first session that I did. But he's saying here, okay, so the program as text is called concrete syntax. I may have mentioned that already in this session. Concrete syntax is what you use to write down and talk about programs. But inside the compiler, we use abstract syntax trees. And so the process of converting from concrete syntax, like text, bytes, and so forth, into abstract syntax is called parsing. And then he goes to say this book does not cover theory implementation of parsing. There is a wealth of literature on that. We're not going to cover that. Now, he provides a parser in the support code for Racket, of course. We don't have one in Gleam because the book is in Racket. So we could possibly look at his parser in the support code later. Let's get our tokenizer done, our Lexer. Okay, so we have. Let's just go down here to. Right, so we have. This is the concrete syntax we're working with. We have these sorts of symbols, plus and minus. Do we not have multiplication and divide? Let me look. No, we just have plus and minus. I don't know why we don't have multiply and divide. I guess they just didn't want to introduce it at this time. Okay, so, and then you have things like and, or, not, if, the comparison operators. So I think that we probably want to make a comparison operator a token, or we can do something like this can be an identifier. That gets ugly because I kind of want to make a special case for, because we're already handling bools as literals, right? We maybe want to handle EQ as a literal, even though it's not the literal like equal sign in Lisp. At least in this variant of Lisp, it's not. Okay. Let's make a comparison operator, and we're going to call it, we're going to make a, now we could use elif.comp, and let's look at that. That might save us some time. So it could be, yeah, this is maybe what we do. Let's do that. So we'll do elif, right? So comparison operator comes out to be one of those. And then it just becomes a question of, do we want to have things like read, let, and or not if as reserved words and not as identifiers? So what's the trade-off there? The trade-off is if we tokenize these as reserved words, then our tokenizer gets a little, our lexer gets a little bit more complicated. Looks like we're already taking on some of that complication, so it might be okay. The other option is if we don't, then what we get are identifiers, and then when we go to parse that, so if like we have a stream of tokens, then we have to like interpret this string or match on this string directly. Question in the chat: is this book featuring Gleam for implementing the parser? No, this book is using Racket to implement the parser, and what we're doing is we're going through the exercises but implementing it in Gleam instead of Racket. So it's a little bit of a flex or a challenge. Okay. So we have some options here, and I think that what I want to do is reserve identifiers for variables, and for user later in the exercise when we get down to chapter 7. We just finished chapter 4. When we get down to chapter 7, people can define their own functions, then identifiers should be for functions as well. So in this case, I think we want to treat these as reserved words. And maybe, yeah, let's call it keyword. And we'll make a keyword type. So that's really just read, let. Let's see, read, let. And I'm going to make these arithmetic operators also keywords as a trick, plus minus. And we have and, or, not, and if. Okay. So now it comes to how do we structure the analyzer. I think we have the data types that we need. We may go back and revise them. Okay, so the lexer, let's look at the example in Nibble. So it does lexer.simple. Let's look at that module, and then it just does a bunch of this stuff. Okay. So I think it's going to try these matchers in order. Right, so that's the sort of thing that this will be doing. I want to look at advanced. Advanced is one that can change what matchers it uses based on the current mode. Actually, we don't need this. We'll use simple. This is more like if you reached a string, and your language supports string interpolation, as an example, or let's say your language supports macros, and you have escape and unescape. You might treat those modes of lexical analysis differently. The quintessential example is string interpolation, though, that like you don't just read from the beginning of the quote until the end quote. You look for other tokens inside the string to find where the interpolation spots are. And then when you're inside that interpolation spot, you switch back to the, the syntactic form, right? That's what advanced is for. Okay. Yeah, or indentation sensitive syntax. That's another good example. If you have something like Python or Haml or any of those or CoffeeScript, where you might want to have things structured based on their indentation, then you could track the indentation and like pass that in to your as context to your tokens. Okay, so we don't need this. Okay, so custom. Current lexeme and one grapheme look ahead returns a match that tells what the, okay. So there's this match type that we need to know about, which is keep, skip, drop, or no match. Keep says accumulate the input and produce a token. Keep match can also transition the lexer into a new mode. Okay. Skip says don't run any additional matchers. Okay, drop says ignore this. And no match says I can't match. So try the next matcher. Okay. We may not need to use that. It's good to know though. So let's start with this is be lexer.simple. I assume there's a run. Yeah. Okay, we're going to do let L is lexer.simple, and then we'll say lexer.run input L. This is not, if it doesn't feel like it's the right way, maybe I feel like I should make a function that does this, and then we just okay, so this is where it will get interesting. So we know we're going to need an integer parser or an integer lexer. So let's do lexer.int. And then we will say that's an integer. We have we can do token. Match exactly the given string with no look ahead. Okay, so we want again, commas there, and that's going to be I see. That's going to be lparen. So we're kind of using the example that they have in the docs here. Token. And generally speaking, what you want to do with lexers is do the strictest matches first, or the simplest matches first. And I'm going to dupe this, and we'll do this is L bracket and R bracket. Okay, so what we want, and just for the purposes of consistency and like talking about talking about order of operations here, these keywords are limited, right? So we definitely, when we turn this input string into tokens, we want to treat these as special, which means we need to parse for them first. Otherwise, they might accidentally become identifiers, and we'll never get keyword variants. So let's do. We're going to put in here. Yeah, and let's not make our. Let's make this lexer.error. We don't need a lexer.error. Oops. We don't need our own error type there. Okay, I think we need to, because we don't want, do we want that wrapped type? Let's look at what that is. Ah, that's actually not so bad. So let's do, if that's not confusing at all. The wrapped type there says that you have, you also have the lexeme that it came from, and the span, where the span is like what, you know, we're tracking the progress through the input, right? Okay. So, and then I want to go back to the example here in the top, because we definitely want to have in here a white space ignore, because we don't care about white space in our list-like language. Okay, so we need to handle booleans. So I want to do this much more simply. I'm just going to hard code these, which is typically what you would do. True. Oh, need commas. Boolean false. If I were doing this in you know, in leaks for Erlang, I would do something like you know, match this string directly and have the token be true. Okay, let's go back into here. So interestingly, they have an identifier. What is this? Start inner. What does this do? This looks like a higher level combinator. Ah, not found. Let's look in main. A nibble lexer. Okay. Let's see if we can find the identifier combinator. And let's look at the tag that we're on. Oh, there's no. Okay, there's no tag there. Okay. Okay, so keyword says match exactly the given string only when the lookahead is matched by the breaker regular expression. Okay, so what we might want to do, rather than say token, maybe what we want to do here is keyword. This is actually going to make it substantially simpler. And then we'll use white space as the actually we don't want white space, we want a word boundary. and because that could be punctuation as well as white space. So let's do the same for false. This will actually make the rest of our stuff a lot easier. No. Getting ahead of me there. Okay. So it says keywords are exact strings like let, but you wouldn't want to lex letter as let and var tter. Yeah. Okay. So we're going to do a bunch of this for our other stuff. So we can do that for all these keywords. Oops. So let's do read, and this will be keyword read. Now read is not technically a keyword, but use let, and this okay, I guess it's fine. The thing is, this cannot be part of identifiers, so I may, at least not at the front of identifiers. So this may be a straight token. These are the sorts of decisions that, I'm sorry, that's not minus, this is and. This is or, not. And one more if. Now, there is a case to be said that we could, do something like make this a map of, of string to keyword, and then, we may do that later. But we don't need to right now. We've got a very small language. Okay, so int is just int with separator, no special separator. Okay, the only thing that we may want to do with ints is, because we're compiling to x86-64, we can't support big nums. But that is something we could do in our parser. We could say integer too large to fit in 64 bits as an error in our parser. So we could have a check on an int token that checks, is this, is this smaller than 64-bit, what can fit in 64 bits. So, okay, we're not doing floats yet. Number parses any float or integer. Okay, so string is just a right, any particular string. So let's look at identifier. Okay, so this is not documented, but it looks like what happens here is start is what is the initial character of an identifier, what are valid, and then inner is what are the rest of them. And so they're saying you have to have at least one, and then inner can be however many of those. So I think that what we'll do here is really simple. Okay, and this is like saying reserved. This is the set of strings that are reserved words. The thing is, we've already We've already handled that. So we should never get to this lexer and find that it has one of these reserved words. But let's do it anyway. Let's say reserved. We need to import Gleam set. We say set from list, and we want a list of strings here. This is, we have read, and we have let, and we have and, or, not, if. Okay, so now we're going to do identifiers. We need to do comparison operators as well, but the problem is that they have some shared prefixes. So we're going to have to figure out how to deal with that. Okay. So let's have, and this is still going to be at the end, I think. So lexer identifier has what is the start. We want to use A to Z. A to Z. So that's going to be it needs to start with an alphabetical character. Oops, and I need to do like that. We could just say they have to be lowercase. I don't know that it actually matters. And then the inner is going to be anything, and actually we just use plus W. That'll allow us to have underscores. And toValue is just identifier. Okay, fine. We can just remove that. I was trying to use the name parameters, but actually that's not how it works. Unless they have an alias out here, you don't get to use the name parameters. Okay, so this is starting with an alphabetical character, and then /W in regular expressions is a number, a letter, or an underscore. So that's what we're going to use there. We're going to want to have tests specifically for that. Interesting. Okay. Gleam has regex in its standard library. We could use it's saying this is an alias of keyword. Honestly, they just look like they're copy pasta. Okay, so we need to handle the comparison operators, and I'm just going to do it with. We use keyword again. They are the same. EQ question mark B, and this is comp EQ, and then let's let's duplicate that a number of times. Let's see here. Okay, and here's a case where we need to handle the stricter versions first. So I'm going to have less than or equal to. and I'm going to have greater than, greater than or equal to first. And then we'll just have less than. Now we can do that. For consistency. And this is going to be greater than, and this will be less than. Okay. You know, there are other options we could have done here. For example, this does a regex for keywords, which means that we could, wait, that's a breaker. It's a straight token. I'm wondering if there's sort of a this is interesting. I don't know if that's fully baked. It's not clear what that's for. Okay, so we could use variable actually. Let's switch this up. Let's use variable. And just pass it our reserved words. That's pretty nice. See if there's any other Lexing functions we want to use in here. Okay. Interesting. So there's some more possibilities of things that we can do here, which is things like sequence types of matches. I don't know that we need to do that yet. One thing that could make this a little bit better is to do something like combine some of these things and and pipe them to something that interprets them. That's a possibility. Remember, in the lexical analysis phase or the tokenizing phase, we don't need to worry about position of the tokens. We only need to worry about what the tokens are. So this is going to get more interesting when we get into the parsing. So let's take a pause here, and we're going to make a test. Okay. and this is going to be EOC passes parse. And we want token, keyword. What else do we want in there? Those are the two types. We want tokens. And then we want to import elif. And we want all the variants of comp, probably. Let's do type comp. Let's do EQ less than, greater than, equal. That's enough, probably. And we're going to need Glee unit. Should. Okay, so okay, so this will be our test. What we want is we want some cases, so we want remember that we don't need to give it valid programs, only valid tokens. So let's make some valid tokens. Plus EQ question mark if those are just types. We don't need to import those directly. We want to get tokens in here. We're gonna need let L paren R paren. I would love to like import star, but there's just not really a way to do that in Gleam. Okay, so yeah, let's do input tokens should be okay, and right, and then we'll take the okay value and should equal, and we're going to make a list of tokens here. So we want L paren R paren, and this is keyword, so we do need to import that because that's a constructor. Keyword let, right? And then we'll have we need plus keyword plus, and we have comp EQ, and we have keyword if. So let's import if. And we need comp. Okay. Okay, so we actually have a problem here. Let's do because we don't know what the spans are, right? So we're gonna take the token and we're gonna say token dot value. That will give us whatever like kind of token it was turned into. Oh, we need, this is EOC language LF. There we go. Okay, so let's run that test. Okay, so we got a failure. No match found. So it didn't, I'm reading that as it didn't know how to analyze let. So let's look at our tokenizer. Perhaps we need to I'm going to make a little utility function that's going to combine these steps. And this is going to take input as a string, and it's going to output a list of token. So this is input, because we're going to do this a bunch. Tokens should be okay. And list.map. Okay. Okay, so we're going to say this is input tokenized. That'll save us some typing, because I want to make some simpler examples. So I want to do, let's just do this tokenized should equal keyword let. And I want to isolate what's going on there, because I think that there's something else wrong. And let's go ahead and inline this one. This will be a bigger example. Okay, so it's still failing on this. So it gets the keyword just fine. What if we do okay, so it has to do with, I think, whatever comes after that token. And I wonder if it's this. Let's look at the combinators we have available again. And this is maybe not so helpful. I'm looking at the contents. I need to look at the documentation. Okay. The breaker is used so you can say what characters should trigger a match. What does that actually, yeah, here we go. What does that actually do? I said I didn't want to look at this again, but here we are. So keyword says yeah, okay, so this is just checking that the next, so it's given a look ahead. This is what's coming next. And it's saying, does this meet? So the problem is we've already consumed the let. This /b is not going to work here. What we need is we need something that is white space or Actually, what we need is something that's not an identifier character. So so we use that variable combinator down here. Where'd that go? Right, so it's using this. So we basically need it to not be this. So we need the negation of that. Let's make ID car is just this. Not ID car. So the keyword, where did it go? When the look ahead is matched by the given. So we're saying whatever character, so the look ahead is empty, which is like, hey, end of stream, that's fine. Or this regular expression that we built from this does match whatever is in the look ahead. So we need to say that this is like, it starts with something that is not an identifier character. Now, for this, yeah, let's just put not ID character in here. And we'll put that in all of these. I think that this will solve the problem. The problem being that if the first character of the look ahead is, say, white space or punctuation, but there's no word character before it, this /b meta meta character is not going to work, right? That's like, hey, I reached the beginning or the end of a word. But if there's nothing before it, then it doesn't know that it's the beginning or the end of the word. It's not going to match. So we're going to use this not ID character. It's a little bit pointless for these others. It's most important on the ones that are actual strings, because we shouldn't ever have, you know, something that is like plus, like that's never going to match, right? Plus and then some strings as an identifier. So we're kind of getting into the weeds here, and I'm sorry, but this should probably fix this. Okay, so we've got a problem with so it's saying in our test we've got this EQ, right? It should consume the whole EQ. Let's look at how that keyword is implemented. The other thing that we could do is, rather than saying not an identifier character, we could say it has to be white space or punctuation. I'm just wondering if this question mark in EQ question mark is becoming a problem. Because it's not a let's see if we can test just okay, so we've solved the let problem. Let's add a keyword if here just to make sure that that works. Let's do EQ tokenized should equal, and this is not keyword but comp EQ, and we'll see if that's an issue. Right. So it's running into this question mark and having an issue there. So interesting. Let's make a white space or punctuation, and we'll say that this is, it's some kind of white space, or it's, we only have plus or minus, right? Let's switch this up and see what happens here. Okay, it's still failing on that question mark. All right, let's cut this down to just the EQ lexer, right? Okay, so now, interesting. So we need to look at what might be going on in terms of ordering. I'm guessing what's happening is it's not. Let's move this up. Let's throw those back in there and see if it still gets past that point. It gets past that point. Add some things back. Before we put all that back, let's put this not ID character in there. Okay, so we're still failing on the, in here, let me put this out to the right so we can see it while we're looking at the code. So we're still failing here, which is where we expect to fail. Let's add let back. Or no, let's add variable back. Oops. Okay, for some reason this variable thing is taking over, and I think we need to start putting. I'm wondering if the order here actually even matters, or if it's doing something else, because. Okay, so this lexer that you create with one of those functions contains matchers, which has a mode, an optional mode in it. So mode is nil there when you do simple. It just returns a list of matchers. So down here in run, Okay, so it turns into graphemes, which is like characters, for lack of a better word. Sets up the state and then calls do run with the Lexer. And then says switch, get the matchers. Right, okay. For the end of the source, but there's still Lexeme left to match. We'll run the final do match, okay? Otherwise, we have one grapheme look ahead to help us with things like matching identifiers and other mode aware tokens. This takes the skip grapheme from the source and calls do match function with it and some other bits. Okay. Could have done this parser by hand, honestly, but I thought that this would save us some time. Okay, so then for okay, so list, it's using list fold until. So this is like keep accumulating things or attempting to accumulate things until the this body here returns no match. And then it's okay, so this list fold until has some flow control stuff in it. Okay, so if you get keep, it stops with that match. If you say skip, it stops with skip. If it says drop, then you stop with drop match. And if there's no match, you continue. Okay, and the fold until is like, this is the accumulator. No match is the default continuator or accumulator. All right, so right, drop is used for comments in white space, which we want to do. The problem here is our okay, so I think I understand this. So it's trying this after this one failed. Why did this one fail is the question. We probably don't need that anchor. The thing is, that variable matcher doesn't include question mark in there, and that's why this is failing, right? But this one should come first, and so it should match exactly. The other thing that we could do is say, rather than keyword, we could use something that's like token. Then we don't care about how it's broken. Let's see if that works. No. If we disable that, does it work? It passes. Okay, so we've got a problem here. I can push this all the way. Oops. I can push this line all the way up to the top, and I don't think it's going to make a difference, which is wild. Yeah, it's matched exactly the given string with no look ahead and produce the given value. Yeah, it's going to put that on one line. Let's see, 3 o'clock. Okay, so we kind of need to figure out. Let's maybe table EQ for a minute, and let's try some of these other things. Okay, so yeah, we got a problem there. Let's remove that. Okay, I want to check that, say, let's check the Boolean. I need to import that. So this will be Boolean true and Boolean false. Okay, that's fine. Let's test the square brackets. Okay. Yeah, let's do all of the keywords here. I'm gonna comment this test out. So we're gonna test integers. We're gonna test punctuation. We're gonna test keywords, and we're gonna test comparison ops, and that's where our EQ will get. We'll fix that eventually, and then we're going to test identifiers. So let's move this up into the keyword section. We're going to do read. Actually, let's just make use of this one. This is going to go in punctuation. So we're going to do read, let, plus, minus, and, or not, if. Okay. Really? Okay. Oh, I need to put a comma in there and maybe it'll help me. Yeah, unqualified. That's what I wanted to do. So read, let, plus, minus, Whoa. And or not. So we're going to need all of those. Okay, so and or not and if. Okay, so that's everything in that. Let's do open paren and close paren. We'll have L paren and R paren. Okay, and then let's test integers. 1, 2, 3, and then yeah. And we need 42 because all their examples use 42. So let's do, and it might actually be useful to do a test for something bigger than 64 bits. 2 to 63, not 2 times 63. -1. So let's put that in there without the why 2 to 63 -1? Because 2's complement. We could do 2 to the 64 as a test as well. Let's do that. Okay. Because for tokenizing, we don't care about integer sizes. Now, we may run into something with JavaScript, for instance, where this is too big. And I don't know what the runtime does in JavaScript, but okay. So we have integer 1. This is dumb, but 3. Let's copy that. Integer. Okay. Oh yeah, I should have turned those commas into underscores. So let's run that. Okay, so that's fine so far. Let's get the comparison ops, which will be we've got greater than, less than, greater than or equal to, less than or equal to. Tokenized should equal. That's greater than, less than. Okay. Okay, so now we have an issue there. So I think that these should be, we should consider making these token. Let's see what happens. And we may need to put them up at the top because the other thing we could do here is say this is keyword, but actually what we want is it should be not the equals character. That's interesting. Okay, let not EQ car. Okay. That's interesting. Um, Obviously, we need this qualifier because we want to produce this token when there's not an equal sign after it. Otherwise, we want to produce the companion token, right? Um, okay, and let's test some identifiers. Let's say A, B, C, something, var 1, 2, 3, 4, and var underscore 3, something like that. I think that this is actually not the case. We probably want to include some additional valid characters in there, like dot, I think, should be a valid character, because we had things like temp dot 1, temp dot 2, and so forth in our compiler. Let's just write this test out, and I'm gonna put this up here in comparison ops. But let's do, okay, so this should be identifier. Let's import that. Identifier. Okay. A and B and C and something and var 1, 2, 3, 4 and var 3, and let's run the test. Okay, so that passes. So how do we fix this EQ question mark? I would think that given the stuff that we have in these others, even if we, like, we put this first, doesn't produce a problem, but let's add a test in here. Is there something about this token combinator? Matches exactly the given string with no look ahead and produce the given value. Let's do a more realistic example in here. Like, let's take something, like, let's take this and actually, I don't think you need the triple quotes. Sorry, I've been doing things in so many different languages lately. Okay, so let's take that string and pipe it to tokenized. So we're going to have the problem, I think, is this is going to fail here. But let's do lparen let keyword let lparen l bracket identifier y l bracket, not l bracket, lparen keyword if Boolean true. You can see how we're starting to get, like I want to get a more realistic example. There's keyword read. R paren, L paren, keyword if, L paren. We're going to have comp equal L paren, keyword read, in sorry, R paren. We're not at the syntactic level yet. And at least it's over here. I can follow along. Okay. R paren after read, and then we have integer 0. Another R paren. And we have integer 777. And we have an L paren. Keyword let. L paren, L bracket. Identifier X. L paren again. Keyword read. R paren, R bracket. R paren. Left paren. Keyword plus. And then integer 1. Identifier X. And then 4 L paren, or 4 R parens, right? Oops. Okay, 4. And then we've got an R bracket and another R paren. And then we have, going into the next line, we have an L paren. We have keyword plus. Identifier Y. Integer 2. We have R paren and R paren. Okay, that was a lot, right? But we've got, this is what it should be. Now we need to deal with EQ question mark, and it is baffling me why our lexers not matching here. Even if we are like really strict with this is the first thing you attempt. Or if we do keyword and say, you know, it's not an ID character after, or it's white space or punctuation. Yeah, so it's somehow getting to this variable and reading and not getting, and it's like, what's this question mark? I don't understand this. If we let's go to the definition of this variable here. This is saying identifier. Start symbol has to be lowercase. We don't actually care. We could loosen that. And then it has to be an alphanumeric character or an underscore. Perhaps perhaps this looks like a string matcher. Let's see what this looks like. So this is starts with whatever this string is. It says char, but it doesn't need to be a character. And then is followed by is followed by huh? I have no idea what this combinator is for. This doesn't make sense. This is like you have something, and then you have any number of things that are not that thing, and then that thing again, and the end. That's not what we want. This is matching on exact equality of the string. Match exactly the given string with no look ahead and produce a given value. Okay, so here's the problem. Token is that the problem though? Does token match only one character? It might. But then how would our other stuff work? Like we have, let's see here. So we're using token here and that works, right? We might need to do our own little combinator here. I feel like this token combinator should just work though. Because if we remove this, I mean, it'll fail on something else, right? It'll fail on that. But like, let's comment out the identifiers thing first. And let's yeah. So if we turn that, if we get rid of that, this matches, which is bonkers to me that this other okay, there's some other things I want to do here. Let's say we want the exact token hash true, hash t, and hash f, because I don't think that they're like, we should not allow you to write identifiers that have hash t and hash f in them. Like, and right, this should token plus should be token. Minus should be a straight token. And so like these can go up because they're stricter. You know, I like to put symbols up at the beginning for whatever reason. It's just like, this doesn't make any sense to me. Why would EQ fail when you suddenly have variable in there? Right, because like you would want to allow um, allow identifiers to start with read, let, and, or not, and if. Like you could say reader, letter, um, andale. Those should be fine. Note, orange, those should be fine to be the prefixes of identifiers. EQ question mark should never be construed as an identifier. And I'm tempted to say here, this has to have white space or some kind of punctuation after it. If there's anything that follows it, it needs to have white space or punctuation. Because I think that if you have, like, if you have EQ question mark A B C D E, I think that should not split into EQ and A B C D E as an identifier. That should be like, I don't know how to parse this. You have an invalid identifier, right? Okay, I'm still getting this no match found. I wonder if I need to do that. I don't think that that's the case because it's not using, yeah. And that's not, it helps if I save it. And that's not going to parse. There might be something where we could do our, or maybe there's just a bug in here that's been fixed and I haven't found it yet. That's really frustrating because I feel like we wasted a bunch of time on something that should have been straightforward. Okay, so this is bumped to 1.1.3. Yeah, we don't need those predicates specifically. That is wrong. I think they meant for that to be identifier. Because variable takes a set of reserves to value. Yeah, that example is wrong. Okay, so this is a function that we may, let's try this. So this takes the mode, which in our parser is nil. And then it takes the current lexeme and one grapheme look ahead. Look ahead. And returns a lexer.match. It's match type. Consume the accumulated input and produce a token with the given value. Okay, interesting. So this would be A is token and mode is nil. Okay, so we can do case lexeme or match lexeme. No, case. Okay, so if it's a string of EQ question mark, then we do keep. Oh, okay, so what maybe the problem is it's not retrying. It's letting it fall through like, hey, this wasn't an exact match, and this one is going, hey, I can get a variable out of there. So we need something that would prevent this combinator from consuming EQ as an identifier. I think what's happening is it's going through and it's like, try all the parsers with one character. Try all the lexers with one character. Try all the lexers with two characters. And it's like, oh, hey, variable, worked. So here we would want to say like we want this to be greedy. That's the problem I'm running into. It's not being greedy when I expect it to be. And then if it's E or EQ, we want to return skip, right? It's like, this is what will make it greedy, right? Skip running any additional matchers this iteration, add the next grapheme to the accumulated input, and run the next iteration. And anything else will be no match. Let's see, lexer dot. Oops. All right, let's see if this fixes our problem. So we're going to say lexer custom lex comp EQ. I thought just the ordering would work. Okay, we were qualifying those. But it's not. So we got all the way through. It didn't. It got an equality error, which means we're missing something. But we should have in here comp EQ. Okay, so I had to make a custom matcher. I shouldn't have, but I had to make a custom matcher where if we have the full EQ question mark, then we keep. If we have any prefix of it, we say skip, which says rerun this matcher with the add the look ahead, add the next grapheme, but don't run any additional matchers. We need to be greedy. So I'm guessing what happens potentially with this variable matcher, which is on top of identifier, is that and there it goes again. So if we go back to definition of that. So this identifier yeah, this doesn't have, unlike keyword, this doesn't have this checks if the okay, so they're checking if there's another character in the extension of identifiers. And if the entire accumulated lexeme matches the identifier regex. Okay, so this inner is just for the extension. Should we continue consuming? So if they both match, so if this is a valid identifier so far, and the next character will match the extension of it, then keep accumulating. If it does not continue the extension, but it's a valid identifier, then check if it's a reserved word. If it is a reserved word, return no match. If it's not a reserved word, then say, hey, this is an identifier. And this is the problem, is that I think that the token doesn't deal with look ahead. So this really should only be used for single. Yeah, this is not strict enough as part of it. So I think we've solved this with our. Oh, the problem is I'm missing an operand on the end. Yep, that's the problem in our test. Oh wait, did we paste it wrong? Yeah, we're missing the operand in our string. But it was in this one, so okay, so let's fix that and see. Okay, so it passes. All right, so it is well past the 2 hours. Most of this time, I feel like we were. Let's re-enable this. Most of the time, I feel like we were dealing with understanding nibble, which is okay. Okay, we don't import Gleam bool. Where is that? Yeah, we don't need that. That's okay. But now we've tokenized. So what we can do is get rid of that we're not using. Right, and this, like, what we wanted here is for this to be greedy. We could probably do something like check if the lexeme plus the look ahead is a prefix of EQ question mark. Let's see. Let's import a Gleam string. Yeah. So let's see if string prefix. Let's see. So if we say something like case string starts with, and we say is prefix. So starts with takes, the first string starts with the second one. So we know that that's what we want to match, and we want to say lexeme look ahead, right? And then we can say if is prefix, right? So that should also work. Yeah. Maybe the pattern match way is a little bit more efficient. But we only want to continue if, you know, we're at E or EQ or the next, or we're at EQ question mark on the next iteration. And then this will also be true, but if lexeme is all three characters, then we'll go this branch. Otherwise, we'll be like, hey, keep accumulating. And then if it's anything else, so if it's not either the full EQ question mark or it's not a prefix of that, then it'll be no match. Okay. This is a good place to stop, so I'm going to make a commit. Let's add all this business. Okay, and then lexer for add a lexer for elif language. Using nibble. And then next time we can do parsing. So here we go. Thank you so much for sticking around, and hope you enjoyed this side quest. Next time we'll look at parsing. It's something that I tend to understand a little bit better sometimes than lexing. Lexing is all about, like, you know, you need to look ahead and, you know, or have what is essentially epsilon transitions is what they'd be called. And what you want when you write your Lexer is something closer to a DFA, and it doesn't look like Nibble is doing that sort of translation. It's just using combinators, and so it's a little bit less efficient than some other things. But it was, honestly, I think it was pretty easy to write this. The hard part was this interaction between expecting an exact match of something and this thing which goes, oh, I got enough things to be an identifier, so you can match that. And then you're left with a dangling question mark. If you were doing this in the classical way, you would write that such that either identifiers can include the question mark, in which case you can special case and turn that into a keyword, or you would put like a qualifier on this one that like it can't be a question mark, which is something we could have done as well. So anyway, we'll do some more next time. We'll get this turned into abstract syntax trees, and which will be really fun, I think. Thank you for sticking around. See you next time.